Okay, welcome everyone. It's a pleasure to have this opportunity to speak to you. So firstly, I want to acknowledge this talk was originally prepared for the Berkeley Logic Colloquium last week. It was at the invitation of Pierre Simon, and so I'm very grateful for them to having this opportunity to speak, and I guess grateful for you for encouraging me to give a second iteration of this talk. So I should say that, so the audience in the Berkeley Logic Colloquium are people who pay attention to the aspects of mathematics that many of the rest of the practicing mathematicians don't. So sort of the formal logic that goes into a rigorous understanding of mathematical proof, or the axioms of set theory upon which many of those proofs are implicitly based. And, you know, there's something a bit curious in that sort of the generic mathematician often doesn't know any of the axioms of set theory and has never taken a course in propositional logic. That certainly was my experience as well. So what was fun about that talk was having an opportunity to speak to the experts as a non-expert. And I want to make clear that I'm sort of very much a non-expert in foundations or type theory, which will be one of the subjects of the talk. So I thought I'd start by reading the abstract, actually, because the title I think can be a little bit confusing, and I just want to make it clear what the project of this talk is going to be. So what the abstract said is that at its current state of the art, infinity category theory is challenging to explain even to specialists in closely related mathematical areas. Nevertheless, historical experience suggests that in, say, a century's time, we will routinely teach this material to undergraduates. This talk describes one dream about how this might come about, under the assumption that 22nd century undergraduates have absorbed the background intuitions of homotopy type theory, also known as univalent foundations. So that's kind of the thesis of this talk. So what I'm inviting us to do today is let's imagine that we're sort of 100 years in the future, and the sort of informal understanding of set theory and logic that undergraduate mathematics students pick up today in our courses has been replaced by some sort of new foundations that are still under development. So this is definitely, there's definitely a speculative aspect of this. And so under that imagining that rather than learning how to write mathematical proofs as is classically done today, we've learned how to write proofs based on homotopy type theory, then I could imagine an advanced undergraduate course on infinity category theory. So the plan is I'm going to sketch this out for you in two parts. Firstly, I'm going to try to give a lightning fast introduction to undergraduate level informal homotopy type theory. And I want to emphasize both the undergraduate level and the informal aspects of that part. And then the second part, I'm going to sketch how we could use those foundations to more simply describe what an infinity category is and prove some basic results of infinity category theory. Experience suggests I'm not going to have a lot of time to get too deep into that, but maybe enough to give a sense of how this dream could perhaps be true. Okay, so I guess let's just go ahead and begin with the undergraduate level informal homotopy type theory. And I should say, right, so firstly, what is type theory? It's a formal system for writing mathematical proofs. It's also a programming language, so I'm really going to de-emphasize that aspect in the talk today. And, but what the way I'm going to introduce type theory here is sort of deliberately informally. Like, again, when you're a mathematics student today, you don't learn how to write a formal proof, though there is such a thing in sort of classical foundations. There's a meaning of formal proof, but we're not doing anything like that. Instead, this is sort of an informal proof, a proof on paper, very much like we write proofs on paper today, but based on these sort of dependent type theory and later homotopy type theory foundations as opposed to classical foundations. And one other thing I would say is if this were meant to be a sketch of a graduate level introduction to homotopy type theory, I would talk about its categorical semantics. So how we interpret a proof in homotopy type theory in the foundations that most of us work in today. But that's really an advanced topic. So understanding the precise relationship between this type of mathematics and the type of mathematics you might be familiar with is very technical and very challenging. And this is a talk for undergraduates, quote unquote. So I don't want to get into that at all. I want to invite you, when you're in this talk, to pretend that you've never learned how to write a proof. You have no idea what mathematics is, and you're seeing all of this for the first time. And if that's too difficult, you can imagine that you're a computer and you're trying to learn how to recognize what a mathematical proof is. That's kind of what we're doing with these computer proof assistants, is we're training a computer who knows nothing about mathematics how to recognize some valid mathematical arguments. Okay, so look at this from fresh eyes and try not to think about how this relates to set theory, because I mean, there is an explanation there. There is sort of mutual consistency proofs, but it's quite a bit more complicated. And I think if we approach this a little bit more naively, we might be able to develop the intuitions more quickly, kind of like if you're, well, I don't know. I'm trying to help everyone learn a new language. Let's just go ahead and begin. So homotopy type theory is based on something called dependent type theory. And this is quite a bit older than homotopy type theory, which is really quite new. So type theory goes back to Russell and Church. Dependent type theory, the rules that I'll talk about today are due to Per Martin Liff in the 1970s. And the point is this all predates the homotopy interpretation by several decades. So what is it? Firstly, it's a formal system of inference rules that can be combined to form derivations. So it is a way to write formal mathematics proofs, so I'm not going to emphasize those aspects so much today. So in dependent type theory, there are 4 kinds of well-formed formulas. So that's a phrase that's familiar to the logicians, but what it means is there are sort of 4 types of grammatically correct sentences. So a proof is built by concatenating a bunch of these grammatically correct sentences in a particular order that's permitted by the rules. And so we're only going to require 2 of those types of sentences. These are technically called judgments. And what the judgments are is I can say that something is a type. So that's one of these sort of primitive judgments, one of these valid things to say in type theory. And then the other thing I can say is that something is a term of a given type. And those are the only 2 types of mathematical sentences we're going to need today. So it's valid to assert that something is a type, and it's valid to assert that something is a term of a given type. All right, so I want to sort of emphasize a color scheme firstly. I'm using red for types and I'm using orange for terms, and red and orange are exclusively used in that way. So if it's in red and you're not sure whether it's a type, it's a type. If it's in orange, it's going to be a term of a given type. I guess one thing to note, to say that something is a term, you always have to say what type it is in, and terms will only belong to a given type. So there's no sort of ambiguity of an element being an element of many different sets. A term just belongs to one type, and you could sort of map it into a different type if you wanted, but everything is sort of well typed. So the way that we're going to write these things informally, an informal proof is what I've written over here. We'll say something is a type or something is a term of a given type. The way it looks formally is in gray. I'm including some of these sort of formal syntax, but again, I don't want to emphasize that too much. So if we do look at the formal syntax, there's something that I've hidden in gray. Gray is a color that I'm inviting you to ignore, but I'll briefly mention what it is. This gamma here is something called a context, and what it does is it declares the types of any variables that appear in sort of the rest of the judgment, the rest of the well-formed formula. So the sort of most basic example of this is in the context of a variable x of type A, so a term of type A, we could have another type b of x where the specification of b of x might depend on the particular value of that x. So an example that would be familiar is there's a Euclidean space, there's a vector space r to the n for each natural number n. So if you have a natural number n in mind, maybe 2 or 3, then you get 2 or 3-dimensional Euclidean space. But once you've declared that n is a natural number, you can think about Rn for any n. And then there's a corresponding thing for terms. That a term might also depend on a previously specified term in a previously specified type, we think of these as being sort of families of types or families of terms. An example is there's a zero vector in any Euclidean space. Though the specification, the definition of that zero vector depends on knowing what n is, because you need to know sort of how many zeros to stick in some sense. Okay, so this is the dependent aspect of dependent type theory, is that types can depend on terms of other things. And I remember when I was learning this for the first time, I found context very confusing, but one thing to think about is when you state a theorem, you sort of say, you know, let n be a natural number and let p be a prime and let a and b be relatively prime integers or whatever. All that let stuff is the context. You're sort of declaring the variables, and then the thing that you state at the end is probably the type in context, but I'll get to that. Okay, so again, type theory is a formal system, so we have these two sort of valid things we can say. We can say that something is a type or something is a term of a type. And then there are 4 different kinds of rules that can be used in derivations. So if I want to stick these judgments together, if I want to stick these sentences together in a way that makes a valid proof that your computer can recognize is a proof, there are 4 rules that sort of tell me when it's valid to assert a judgment. So they're called the Formulation Rule, the Introduction Rule, the Elimination Rule, and the Computation Rules. And I'll introduce all of these in an example. So what the Formulation Rule says is it said, if I'm given 2 types, A and B, then I can form a new type. Here I'll tell you about the rules for something called the product type. So the Formulation Rule for the product type says, given types A and B, there is a product type A times B. And product type is just a name. This is just a notation. The symbol doesn't mean anything in absence of the notation, but the other rules that I'll tell you about, the introduction, the elimination, the computation rules, are what makes this behave like a product that you may be familiar with. And in gray, we won't see this very much again, but just very briefly, there is a way to sort of make this formal so that proofs now look like derivation trees, and this is what this rule looks like from that perspective. So if I'm given a pair of types, then I'm allowed to assert that I have this other type. Okay, so then the introduction rules, what they do is they introduce new terms and the types that were just formed by the formation rule. So now that we have a product type, we might want to have terms of the product type. And what the introduction rule says in the case of the product type is it says that if I'm given any terms, little a and little b and b, then there is a term little a comma b in a times b. And again, this pairing thing is just notation. So I could have written this in a different way. I could call this p if I want, but it's good to indicate it had some dependency on a and b, because it certainly does. So the introduction rule says that whenever I have terms of the given types, I can pair them and get a term of the product type. All right, so then the next type of rule is something called an elimination rule. And what it does is it allows us to use these new terms. So it says if you're given an arbitrary term of the product type, so an arbitrary p, then what the elimination rule for the product type tells us is that from this we can get a term of type A and also a term of type B. And again, I'm using notation for this just to suggest to those of you who are familiar with products what this would look like. So this you can think of as the first projection of P. And this would be the second projection of P. And then there's a final class of rules, the computation rules, that relate 2 and 3. And this is going to say, in the case of the product type, that if I pair terms A and B and then take the first projection, I recover the term A, and vice versa for B. And then there's also a computation rule that says that if I take a term of the product type, I take its projections and I pair them back, I recover the original term. So I haven't written that out because the computational aspects of type theory aren't going to play a big role today, though certainly they're very important to thinking of type theory as a programming language. The other reason I haven't written it is it requires the other 2 types of judgments. I mentioned there are 4 kinds of judgments, and I only told you about 2 of them. And I'm just trying to sort of limit the number of things that we have to pay attention to follow this talk. Anyway, so I apologize for de-emphasizing the computational aspects, but I think that's the right thing to do. Okay, so this is sort of the basic bones of type theory. I'd like to pause for a moment in hopes that somebody will ask me a question.
So I guess for the computation rules, is it like valid to think about it as the intro rules and elimination rules are sort of inverses of each other and they're like one-to-one?
Right. So, so there's a reason, right? So that's a great question. So, I mean, in general, the introduction rules are, there's a sense in which, so the introduction rules are kind of about mapping into a type. Because of the presence of context, what the introduction rules tell you about is the functions that you have from an arbitrary family of types into the type that's just been formed, while the elimination rules tell you about the functions mapping out of them. It's better not to think, though, in terms of these being inverses or establishing a bijection between certain things. I mean, there's a sense in which these rules give something like the universal property of the Cartesian product that you might be familiar with, but there's also a sense in which they don't. And I'll get to that a little bit later. So one of the reasons I'm de-emphasizing the computational aspects here is there are two sort of notions of equality in type theory. There's one that would be expressed by the computation rules, which is, sort of, can a computer reduce a given term to another term? And then there's the sort of equality that you prove, and that's the one that's going to be important today. So, and this is one of the most confusing aspects for sure. So I'm trying to avoid the confusion by just not acknowledging that there is a thing to be confused about here. Yeah, so that is a good question, and I realize I didn't give a very satisfying answer.
That's cool. Thank you.
Sure. Other questions?
I had a question. I was curious about the gamma. Is that similar to like a consistent theory of sentences in terms of some language, or?
I have no idea what that means, so I don't know. Maybe somebody else does. Yeah.
Oh, okay. Thank you.
Sure. Okay. Right. So let's try and go on a bit more. So let me give another example of a type. So there are many type forming operations, which allow us to do many different mathematical constructions. So another really important one is something called function types. And again, they have formation, introduction, elimination, and computation rules. So the formation rule says that if I'm given types A and B, there is a type, and this is the standard notation for that type. But again, it's just notation. It's a type which is called the function type. The introduction rule in this case is a little bit complicated, so let's just sort of pretend that we understand it. But it says if in the context of any term, there is a way to define, so in the context of any term of type A, there's a way to define a term of type B, then you can use something called the Lambda Abstraction. This is, to mathematicians, it would be more familiar as saying sort of little x maps to B of x. This is just a concise notation for that. But if there were a way to produce a term of type B from a term of type A, you can sort of package that into a function A to B. This is what that looks like a little bit more formally. And then the elimination rule is a little easier in this case. It says that if I'm given a term of the function type, note this is a very convenient notation for that. And if I'm given a term of type A, then I can evaluate the function at that term and get a term here. And the computation rule will say if this f is defined using this lambda abstraction and then applied to this a, what I should recover here is b of a, for instance. Okay, so so you can imagine, I know these rules might be hard to think about, but you can imagine teaching a computer about these rules. But now you want your computer or your undergraduates to know how to prove theorems. And if we were talking about sort of ordinary kind of classical foundations of mathematics, there's sort of two aspects of proving theorems. Firstly, there's the underlying propositional logic or predicate logic and first order logic. And then there's also sort of axioms of something like set theory, and sort of combining the set theory and the logic is how we prove theorems. One of the things that's interesting about type theory is I've told you the whole story. So we have these judgments that say, I can say that something is a term or something is a type, and I have these rules, and that's it. So so you could ask then, well, how do we state and prove theorems? Well, it's exactly by sort of doing the things that we just mentioned. So if I want to prove a proposition, what you do is, well, first, if I want to state a proposition, what you do is you construct a type whose sort of form, I guess, encodes the statement you're trying to prove. And then to prove the proposition, what you do is you construct a term in the type that's encoding its statement. So this sounds very abstract, so let me just illustrate. So here's our first proposition. It says that for any types P and Q, sort of more formally, this is saying we have a P and a Q in the context. There is a term in the type P times P implies Q implies Q. But now let me tell you how I would read this. So this is going to be what we're so I've called this term modus ponens. What we're proving is one of the tautologies that are familiar from propositional logic. And what I'm trying to illustrate here is that we can think of this type, which you can build from P and Q by applying the formation rule for function type and the formation rule for product type. We can think of this type as encoding the statement that says P and P implies Q implies Q. So right now it just sort of looks like that because this symbol is similar to the and symbol, and this symbol is similar to the implies symbol. But the point is that the rules that I've introduced here, the rules for the product type and the rules for the function type, mean that it makes sense to think of this in this sort of logical way. And I guess the proof is sort of by experience. Once you the proof that this interpretation sort of makes sense is sort of by experience. And I think let's just try and give an illustration. So what I'm going to do is I'm going to construct a term of this type. This term I'm going to call modus ponens, that you should think about as being some sort of constructive proof that P and P implies Q implies Q. Okay. So let's, and we're going to do this just by applying these rules. So the task again is to construct a term of a given type. So to construct a term of a type, we can use the introduction rule for that. So that's the first step of the proof. So by the introduction rule for function types, if I were to try and construct a term of this type, what I need to do is explain how to use a generic term, X, like a variable term in this type, and then produce a term of type Q. That's what this introduction rule says. I can get a term of a function type by explaining how to use a term of its domain to produce a term of its codomain. Okay. But by the elimination rule for the product type, so if I have this term little x in a product type, I can take its projections and get two terms, a term of type P and a term of type P implies Q. And then by the elimination rule for function types, if I had a term here and a term here, I can evaluate this function at that term and get a term of type Q. So packaging this all together, if I were writing this in a computer, I could write this proof in one line. I would say we can define modus ponens to be the term that's given by the lambda abstraction, lambda x dot second projection evaluated at first projection. Okay, so that's a little wacky, but it really is kind of the way that we understand modus ponens. So here I'm assuming P and P implies Q is true. From that assumption, I can conclude that P is true. So this PR1X is a proof of whatever proposition is encoded by the type P. And this PR2X is a proof of whatever proposition is encoded by this type P implies Q. And now the rules for the function type say that really thinking of this as an implication is valid. So modus ponens is somehow encoded in these rules. And actually, there are a lot of tautologies from first order logic that can be proven similarly, that can be proven just by applying the rules, so on. Okay, so, right, so now I want to get back to the question about mathematical equality, and this is definitely the most subtle aspect of this story. So we have this idea that I've illustrated here that a proposition, a mathematical proposition, can be encoded just by forming a type that looks like its statement. So if we've got implication, we've got conjunction, there are a whole lot of other types that correspond to things like disjunction and the quantifiers. We will see the quantifiers a little bit later. But if a lot of mathematical statements are of the form, you know, x equals y. And if we want to talk about those sorts of statements in type theory, we need a type for that. And that's what these identity types are all about. So these rules were devised by Martin Lüff in the 1970s. And let me just sort of tell you what they are. So there's a formation rule that says that if I'm given any type A and any two terms, x and y of type A, then I'm entitled to form a type. And here's the notation, x equals y over A. And this type, again, is asking the question, is x equal to y? So that may or may not be true. You can ask whether 0 is equal to 1. That's definitely a valid type. But if 0 and 1 are terms of the type of natural numbers, for instance, there won't be a proof of that. There won't be a term in this type. Okay, so the formulation rule again says that if I'm given any two terms of the same type, it is valid to ask, are they equal? I may or may not have a term in here, so I may or may not have a proof that x is equal to y, but it's certainly a valid question. Though it wouldn't be valid if x and y lived in different types. All right, the introduction rule says that, well, there's one case that we know for sure that this is true, and that's in the case when it's x and x. So the introduction rule says, given a term x, then there is a term which is called REFL x in the type x is equal to x. And that's the only introduction rule for the mathematical equality type. So that's the only term that we're ever guaranteed to have as a proof of reflexivity. Sorry, the REFL is for reflexivity. This is a proof that x is equal to x. So the elimination rule for the identity type, I declined to write out because it's a bit complicated when you're seeing it for the first type, but it can be packaged into a proof technique, which I'm going to call path induction. And I'll explain the name path in the path induction later on. So I promise that's coming. So, right, so this is a proof technique, and really it's an encoding of the elimination rule, which I'm not spelling out. And I'll state the proof technique and then we'll practice using it. Sorry about that. Right, so the proof technique says that if I'm given any type family that depends on two terms of type A and a proof that x equals y, in other words, a term of this identity type. So B, X, Y, P is any other type. So any type that you can form given the data of two terms of type A and a proof that x is equal to y. Then if I'm trying to produce a term of this type, for, again, any x, y, and p, it suffices to do so only in a special case. So it suffices to assume that y is x and p is REFL. Okay, so that's the statement of the path induction principle. And I know this is confusing if you're seeing this for the first time. So let's just see an example of the sort of way it can be used. And you can imagine, well, maybe remember being an undergraduate, when you learn about mathematical induction for the first time, the technical statement of mathematical induction is very complicated and it's very confusing for a while, but after you've done 10 exercises writing induction proofs, you sort of start to get the hang of it. And path induction is similar. So because you're seeing this for the first time, it's going to be a little confusing now, but you might imagine that if you wrote 10 proofs using path induction, you'd start to get a hang of it. I'll give 2 proofs today, which won't be quite enough, but we'll start us on the path. Okay, so firstly, the rules for the identity type guaranteed that this identity relation is reflexive. So we have an introduction rule that produces a reflexive term, but we haven't mentioned symmetry or transitivity, and the reason that is that those follow. So the elimination rule, this path induction principle, is going to be powerful enough to prove symmetry, which I'm stating as this. So what does symmetry mean? It says for any terms x and y in type A, I can form a type, which is in red here. This is a single type. It's the type, so it's a function type that relates this identity type to this identity type. And the way you should think about it is this type is asserting the proposition that x equals y implies y equals x. So the statement of the lemma is really this type. And the proof of the lemma, I'm going to construct a term now of this type, like we constructed the modus ponens term just above. What I'm going to do is I'm going to construct a term of this type, which is then a proof of the implication that's asserted by the type. Okay, so I'm proving symmetry of equality. How do we do it? So I'm just going to apply all the rules. So by the introduction rule for function types, if I'm trying to get a term of a function type, I'm allowed to assume I have a term of the domain. So I'm going to assume there's a proof P that X is equal to Y. And then my task is to produce a term of this type here. Okay, so that might look challenging because our introduction rules don't give us ways to produce terms of type Y equals X, but that's exactly what path induction is good for. So by path induction, what this induction principle says is that if I'm trying to inhabit the type family, the notation here was BXYP, but here it's this type Y equals X, whose statement depends on X and Y and this proof that X is equal to Y, then it suffices to assume that Y is X and P is REFL. So it suffices to only inhabit sort of special cases of this type family, the ones where it's X equals X. And in that case, I can do that because the introduction rule for the identity type tells us I have these terms REFL X. Okay, so this seems crazy, but this is sort of the magic of path induction. You can reduce a lot of statements involving equality to just trivial cases of reflexivity. All right, let's see another. Yes, please go ahead.
Our definition of B here didn't actually use P. Is that normal?
So this sort of statement of, it sort of does include P and it doesn't include P. So you're right that in the formation of the type Y equals AX, P is not required to form that type. But having a proof that X equals Y is definitely required to make this path induction principle work. Right, the reason that I'm allowed, this is going to be easier to, this will be a little bit easier to explain once we have the homotopy interpretation yet. Right, so let's imagine real quick that A is the natural numbers. So the terms of the natural numbers are the 0, 1, 2, 3, 4, and none of those identity types are going to be inhabited. So 3 is not equal to 4, 4 is not equal to 5, et cetera, et cetera, et cetera. So path induction applies in that case, and it would sort of allow us to reduce a term or I could apply this proof to that case, to that particular case. And it says exactly as before that to inhabit the type family BXYP, which in this case is like saying Y is equal to X as terms of the natural numbers, it suffices to assume blah, 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 blah. But the point is, I'm only going to, when I'm trying to prove this implication after all, the only time I'm going to be trying to prove that Y and X are equal as terms of type naturals is when X is equal to Y as terms of type naturals, if that makes sense. So when I don't actually have a P in here, this will be empty, and so this kind of implication is automatic. It's that sort of thing. So so you're right that the formation rule for this type does not require P, but the path induction principle, it does require P in some way. So the reason, the reason that I'm allowed to conclude this the reason that I'm allowed to conclude that Y is equal to X from the special case where Y is sort of judgmentally equal to X, where I've substituted X for Y, is because of the presence of this P. That's maybe a better way to think about it. Great. Okay, so here's an even more complicated instantiation of path induction. So again, if I were teaching this to undergraduates who are learning this for the first time, this proof would be 5 times as long as I would spell out every step. But here's kind of a high-level overview of this. So similarly, we can prove the transitivity of equality. So for any terms x, y, z of type A, if x is equal to y and y is equal to z, then x is equal to z. And here's how it would go. So firstly, the statement is encoded by this type here that I've formed by applying the formation rules for identity types and for function types. Now, by the introduction rule for function types, which I'm, I guess, applying twice, if I want to get a term of this type, then I'm allowed to assume that I have a proof that x is equal to y. And then I'm also allowed to assume that I have a proof that y is equal to z. And now what I'm trying to do is get a proof that x is equal to z. That's allowed to use these 2 proofs as input. And there's several ways to do that, but one way is to do a double path induction. So I'm going to do a path induction on P and on Q, and use that to assume that Y and Z are both X and P and Q are both reflexivity. But in that case, by the introduction rule again, I have this reflexivity term, and I'm only trying to inhabit the reflexivity case. So that's one way to do this. It's also possible to prove this with a single path induction, and that might be something that's fun to explore on your own. Okay, maybe this is a good place for questions too before I get onto the homotopical interpretation.
Hi. So is what's the proof for path induction?
Right. So, I mean, essentially path induction is a packaging. That's a great question. Thanks for it. So essentially it's a packaging of the elimination rule. So had I written out the elimination rule formally, so here we wrote out the introduction rule formally. Had I written out the elimination rule and then just read it to you, it's essentially this path induction. So that's one way to say it. What's less clear is that it's a valid rule. So the elimination rule is more or less just exactly this path induction. So what's surprising, I mean, this was really a very insightful definition of Per Martin Liff. What's surprising is that it's a valid rule, and I will say a little bit about that using the homotopical interpretation. So maybe I'll go there right now. So really, it is just the elimination rule. It's just sort of how it's given to you in type theory. And what's crazy is that it's actually reasonable. Okay, so let me try and explain that. So the homotopy type theory is sort of a new way of thinking about dependent type theory, which had been around for several decades. And it has to do with this new way of thinking about what we're doing with these types and terms and all of that. This is this homotopical interpretation of dependent type theory. So this should be some sort of intuition for type theory. That what type theory still means is it's the rules that I've been talking about before. It hasn't changed. We're just changing how we think about it, what the basic intuitions are. So the intuition in this homotopical interpretation is that we can think of a type as being something like a topological space, but that's not quite right. It's really something more like a homotopy type, which is kind of a flabbier way to think about topological spaces. So here I've drawn a space that looks like a surface of genus 2. That's an example of a topological space. A term in the type now we're thinking of as being like a point in that topological space. And now we're explaining this path and path induction. If we had a term in an identity type, so to form this identity type, X and Y must be terms of type A. So those are interpreted as points in the space A. Now we're going to think of a term in an identity type as a path from X to Y in A. So here I've drawn a picture of a path P from the point X to the point Y in the space A. And here's some things that are good about that interpretation. I mean, firstly, I can apply these formation rules iteratively. So once I have two terms X and Y in type A, I can form the identity type, and then I can think about terms in the identity type that are paths from X to Y. But if I have two paths from X to Y, this P and this Q, those are then both terms in the same identity type. So I can form an identity type that is asking the question, is P equal to Q as paths from X to Y in A? This is an iterated identity type. And I can imagine having a term in that. And so what should that be? Well, a term in a path type should be a path between paths. And there's a name for that in sort of algebraic topology. It's called a homotopy. A homotopy is a path between paths. I've drawn a picture here. I really should have given it a direction. This you can imagine as being a path of paths from P to Q, where P and Q are both paths from X to Y in A. That's sort of a picture of a homotopy. And one of the interesting things about this interpretation is, so in the picture I've drawn here, some paths are homotopic. So P and Q are two paths from X to Y, and there is a homotopy between them. You could prove that P is equal to Q as proofs that X are equal to Y as terms of type A. But other paths are not homotopic. So I could consider the composite of Q with R, where composition, by the way, is the new way to think about this transitivity proof. I can compose a path from X to Y and a path from Y to Z to get a path from X to Z. So I can imagine applying that to this Q and this R and get a composite path from X to Z. But here I've drawn another path from X to Z, which I didn't give a name. And because of the presence of this hole, those paths will not be homotopic. So you can imagine from this homotopy interpretation that you might have two terms in this iterated identity type, or two terms in an identity type. So two paths from X to Z in the picture here that are not equal, so that the iterated identity type will not be inhabited. And this was an open research question in type theory for a long time. There was this conjecture called indiscernibility of identicals that said, if I have two proofs P and Q that X are equal to Y, then I should always be able to prove P is equal to Q. People thought you might be able to use the rules of type theory in a very clever way to prove this, and they weren't able to do so. And the reason they weren't is there are now these counter models. It was shown by Hoffman and Stryker, firstly with a groupoid model, and then later with this homotopy model, that you shouldn't expect to be able to prove necessarily that two terms of an identity type are equal. So that's one cool thing about this homotopy interpretation. So from this point of view, the two properties of the identity types that we've just discussed, this symmetry and this transitivity, now become reversal and composition of paths. So if we think of P, a proof that X equals Y as a path from X to Y, then a proof that Y equals X is a path from Y to X. And what this symmetry proof above was explaining is how to reverse a path, sort of proving that every path can be reversed. And similarly, transitivity, as we just discussed, is a composition rule for paths. And of course, all of these apply for any, there were this context here, this reversal property applies for any X and Y in A. So A could itself be an identity type, and P and Q could then be proofs of equality, and then these could be iterated identity types. So in other words, I get the same reversal and composition rules for homotopies. These were the paths between paths. And there are also higher homotopies. So if I had an H and a K, two homotopies from P to Q as paths from X to Y and A, I could form the identity type that is asking whether H and K are equal as homotopies. And a higher homotopy would be a term in that type. And this just sort of goes all the way up. And there's a way to sort of make all this precise. This is a theorem of Peter Lumsdaine or Benno van den Berg and Richard Garner, which say that types inherit the structure of something called an infinity groupoid. And the way you should think about an infinity groupoid is it's sort of something like this. It's got points and it's got paths and it's got paths between paths and paths between paths and paths and so on and so on and forth. And you're always allowed to, you can compose at each level and invert things at each level. And then there's some sort of associativity principle and there's some sort of identity principle, though those relationships are generally hold up to higher paths rather than up to kind of strict equality. Whenever we talk about equality going on, we're going to be using this sort of equality that's given by this identity type. So to prove, I guess what I'm trying to say there is to prove that P composed with the reversal of P is the reflexivity proof. What you would do is you would construct a term of an identity type. So you're constructing a homotopy then between the composite of P with the reversal of P and the identity.
So, is the model for infinite groupoids that they used equivalent to kind of complexes, or is it some other model?
Right. So, I mean, there's a sense in which all models for infinity groupoids are equivalent. They did not use the concomplex model. They used something that's sort of more globular, because that's more that's closer to the sort of shapes that are involved in this presentation. But if you Google, you'll be able to find the paper reference. Okay.
So if we have two paths that are not homotopic, would that be kind of interpretable as we having two proofs that are fundamentally different in a way?
Yes, absolutely. That's right.
Okay.
That's right. Great. So in the homotopy, so this is one aspect of this homotopy interpretation. So, I mean, one of, in my view, the very compelling aspects of this homotopy interpretation is it gives us a really natural way to think about these rules for the identity type that predated the homotopy interpretation by like 4 decades. But it continues to sort of all of type theory. So there are other formation rules there are other aspects of dependent type theory that we haven't really emphasized that I want to introduce now. So firstly, we talked about this notion of a type family. So we can have a family of types that varies depending on a term in a given type. And the interpretation of that in homotopy theory is something called a fibration. So what a fibration is it's 2 different spaces. There's something called the base space, and that's the type here. So here in the picture, I've drawn the base space as a circle. And then what a fibration means is there's a total space. So there's another space here. I've drawn a cylinder, but I should think of this as being a family of spaces over the circle. So for each point in the circle, the fiber of the fibration, there's some space above it. In that case, that's this interval. And yeah, I mean, that's kind of the vague idea of a fibration. So there are 2 formation rules for these type families that I want to briefly mention now. There's one called a dependent sum that takes a type family and forms a new type that's denoted this way, that's interpreted as the total space of the fibration. And what its introduction rule says is that to give a term in here, it suffices to firstly give a term of type A, so like this little a downstairs, and then also give a term in the fiber, so give a term in the type B of A. So that would be like giving a point along this thing. So the terms in this total space are pairs comprised of a term in the base type and then a term in the fiber over that base. And then the other formation rule is something called the dependent function type, which this is the notation for that. And this is a less familiar concept. It's the space of sections. So a term in the dependent function type, that's this little f, what it will be is it will give, I guess by its elimination rule, what it will give is a function that takes a term, maybe little a and A, and then produces a term in B of A. So here, so there's a name for that. It's a section. It's a continuous section. So a function that maps from this circle back into this total space in such a way that each point lies in the fiber over the point on the circle is like this thing that I've illustrated here, this sort of wavy circle that's mapping through the cylinder. Okay, so we have these things called dependent sum types and dependent function types. We will see them later on. I should note that these are generalizations of the types that we've seen already. So it's possible that we have a constant type family that I guess came up above. So maybe B is just a type that doesn't actually depend on this X at all. And in the case of a constant type family, this is exactly the product type, or this reduces to the product type. And this reduces to the function type. So I should think of this as some sort of generalization of the product type construction and some sort of generalization of the function type construction, where the type of the second bit might vary depending on what the first term was. Okay, so one of the useful things about this homotopical interpretation is that it then inspires new definitions. So all of the definitions that I'm about to give, these make sense in the dependent type theory per Martin Luft's dependent type theory that we'd already introduced. So I'm not, as yet changing any of the rules of type theory, but I'm using these homotopical ideas to give new definitions in the type theory. So in homotopy theory, what it means to say that something exists uniquely, or to say that there exists a unique term of type A, means that the space A should be contractible. Contractible means it's equivalent as a space to just the point, the one point space. And so here's a type which is encoding the statement that A is a contractible type. So to show something is contractible, or to show that something exists uniquely, what you would need to do is, or the way you prove a unique existence usually is, firstly, you prove that A is true. You prove that there exists something in type A. So that's this part here. If I were to produce a term of this type, what I would have to do is firstly construct a term in type A, and then show that for every, so this dependent sum you should think of as being something like existence, though really it's more of a constructive existence. And then what I would need to show is that for every x in A, this product you can think of as being like the universal quantifier for all, then I can prove that A is equal to X. So you can sort of naively read this as a statement of the usual strategy for proving something exists uniquely. Firstly, you show that there exists a term little a in A, and then you prove that if you had another term X in A, that A and X are in fact equal. But under the homotopical interpretation, this becomes, well, this is the statement that the type A is contractible. And this is one of the things that we're going to use later on. I'm going to say something exists uniquely. And what I really mean by that is that a type formed in this way is a contractible type. Okay.
Sorry, may I ask?
Yes.
I'm seeing this and I'm thinking, but this looks more like A is connected, not contractible.
Yes, absolutely. So that's a great observation. You're totally right. So this definition is due to Voevodsky, and when Voevodsky first started telling people about it, everyone was surprised because it absolutely looks a lot more like path connectedness. I should say that from the homotopical point of view, a way to understand what this type theory is it's you're sort of synthetically doing homotopy theory, and in this sort of synthetic language, sort of governed by the rules of type theory, everything is automatically continuous. So while it looks like here to construct a term of this part, I would just be constructing a path from a path from each term X back to A. Really, I'm constructing a continuous family of paths that's sort of continuous in this space A down here, and that's what makes it really a contracting homotopy rather than just a path. So yeah, everything's kind of more continuous than you think, and sort of automatically as somehow enforced by this homotopy interpretation. But it is a bit of a surprise. That was a great question. Great, and then the last thing I want to say about this homotopy interpretation is it also, there's a natural definition of when two spaces are equivalent or homotopy equivalent. And now that we're thinking about types as spaces, we can import that definition into homotopy type theory. And the definition is going to, again, this is going to look a little differently than the definition you'd expect. And I want to try and explain why that is. So firstly, I'm going to define, what I'm doing here is I'm defining a type that is asserting that the types A and B are equivalent. So if I had a term in that type, that term should be a proof that A and B are equivalent as types, where equivalent is in the sense of homotopy equivalence. Okay, so let's try and read this type. This is the sort of thing that will get easier with practice. So a term in this type would provide the data, I guess by the elimination rules, a term in this type would provide the data of, well, so firstly, let me just read it out in words. So the type A is equivalent to B says that there exists a term F, a function F from A to B, and then there also exists a function G from B to A, so that for all little a and A, there is a path from G of F of A back to A, or really this is going to be a homotopy because this is a continuous family of paths as before. And similarly, there exists a function H from B to A, so that for all terms little b and B, there is a path from F of H of B back to B. Again, this is a homotopy. Okay, so by the elimination rule, if I had a term in this type of equivalences, what it would give me is firstly a term F in the function type, so a function from A to B, and then two terms of the function type from B to A, the G here and the H here. I'd have two terms like that together with homotopies. That's sort of a natural way to think about a term in these sort of dependent function types. So this is a sort of continuous family of paths from G of F of A back to A, and a continuous family of paths from F of H of B back to B. So if I had this data, so if I had my F and my G and my H and my alpha and my beta, then you can compose these homotopies and get a homotopy between G and H. So you can prove that G and H are really the same function, or at least homotopic functions, a posteriori from the data here. So that might suggest that this was kind of a more complicated definition that needed be. You know, it seems strange that I have two dependent sums in here rather than just a single one and have it like that. But there's a reason to define equivalence to be in this way rather than that way. And this is because, you know, we had this idea that I stated above, that we're thinking about a mathematical proposition as being encoded by a type. So we have a type that encodes a mathematical statement. But there's something a little bit subtle there. The way in classical logic we think about a proposition is something that's either true or false, and that's sort of the end of the story. But now with this homotopical interpretation, a type is really a space. And as we were discussing, we can have proofs of points in that space that are not connected by a path, or we can have proofs that are not equal. And so there's some sort of higher complexity level sort of sitting on top of the propositions. And it's sort of in attention to this higher homotopy or higher proof theory aspects that we've preferred this definition of equivalence to the one that you might have guessed first. So I can say that sort of more precisely as follows. So if I define an equivalence to be a function f from A to B that is equipped with a priori distinct left and right inverses, so that's this G and H that might be different, then it follows that if I had any two terms in this type, so if I had any two proofs that there exists a G and a homotopy and exists an H and a homotopy, then I can always prove that those proofs are equal. So in other words, this type here is, it's called a mere proposition. This type is either inhabited or contractible. So the data that would equip a given function with an equivalence in this sense is unique in the sense of homotopy type theory if it exists. Whereas if I had expressed the property of f being an equivalence in this more naive way, just saying there exists a single function g from B to A together with a pair of homotopies, this type might have distinct terms. So this type might have some sort of higher homotopical structure. Whereas this type is really just encoding the proposition as we usually understand it, something that's either true or false, that f is an equivalence. Okay, so that's, I know that's not sufficient as an introduction to homotopy type theory, but that's all you're going to get today. But I'll stop here and
ask a question?
Questions, please. Yeah.
I thought I heard you say that this. Can you hear me all right?
Mm-hmm.
Oh, I thought I heard you say that that it's a mere proposition, meaning it's either inhabited or contractible.
That's correct.
But did you mean either uninhabited or contractible?
Yes, sorry, that's correct.
Okay.
Yeah, absolutely.
I'm not sure if I misheard. I just wanted to clarify. Thank you so much.
Yeah, thanks. Right, inhabited means there is a term. Yeah, uninhabited would mean, right. Thanks. Yeah.
I have a question.
Sure.
Why is it desirable that having these inverses be a mere proposition?
Right. So one advantage there is I can understand if I define the type of equivalences in this way. It's kind of a subtype of the type of functions. So this is right. I guess this is giving it a tighter relationship to the type of functions. So that's maybe one way to say it. I guess, so if I were, you could also imagine building a more complicated type where one of the hypotheses, so one of the pieces of that type is that your given math is an equivalence. And you want this more complicated type to be as simple as possible. So you want to have the hypothesis that f is an equivalence to be one of these propositions, to be sort of simple as possible, so that a term in that is a contractible type and you can kind of contract it away and so on. So, right, I mean, this is the sort of thing that matters. If I'm building a very, very complicated type and one of the hypotheses is that f is an equivalence, I want to say that in as an efficient way as possible. So you definitely want to phrase it using one of these mere propositions rather than something more complicated. Otherwise, it's just giving you all this data that you're carrying around. Maybe another thing to say is there's a philosophy that sort of doing mathematics and type theory is like doing proof relevant mathematics because, all of these terms are proofs and which term you have might matter. it's just the sort of thing that you start to realize that you should attend to. Right, so that, I mean, I guess there's a reason, there's a reason that I preferred this particular proof of transitivity as opposed to a different proof that required only a single path induction rather than a double path induction. It's kind of an aesthetic that the community shares. So.
Should it be obvious why the second one might not be contractible?
No, it's no, and it's, right. It's not at all obvious, but it's the sort of thing that a homotopy theorist might have experience with. You know, and it might also be contractible too, depending on what A and B are. So to have a priori distinct terms, you know, A and B need to have some kind of non-trivial higher homotopy. But I think, I guess kind of all I wanted to say is one of the things that I found cool about homotopy type theory, one of the things I found compelling is, you know, there are a lot of logically equivalent statements. I mean, if there is a term of this type, there is a term of this type. And if there is a term of this type, there is a term of this type. So that's the sense in which these are logically equivalent that are not sort of homotopy equivalent. So, you know, how this works is in, you know, sort of mathematics, you learn a lot of equivalent definitions of the same concept. And what homotopy type theory is saying is that some of them are sort of genuinely equivalent in the sense of defining equivalent spaces, but others aren't sort of equivalent in that strong a sense. They're more merely logically equivalent. And I think that's an interesting thing to know.
Can I ask you to give an example of this, either in that two equivalent definitions are not really equivalent, or in that two proofs are really different?
Right, so the two equivalent definitions that are not really equivalent are the two here. So that this type in red and, this type and this type are logically equivalent, but not really equivalent. So that's the only example I'll give you right now. So I recently learned an example of two proofs that are not equivalent. So here's a tautology from classical logic. If I have, so P and Q implies P or Q is a true statement. And you can imagine two different ways of proving that. You can prove that P and Q implies P, which then implies P or Q. Or you can prove that P and Q implies Q, which implies P or Q. So if I want to do something like this in homotopy type theory, I have to say what I mean by or, and there are different choices you could make. If you interpret or as something called a coproduct type or something like a disjoint union, then those two terms that I've just described are provably not equal, you know, for arbitrary P and Q. So that's a sort of example.
Interesting, thank you.
Sure. Okay, so in the last 25 minutes or so, let me try and give you some sort of introduction to infinity category theory. So again, you know, this won't be sufficient. This is only, you know, ideally this would be a semester-long course in infinity category theory. So really I'm going to give you an impression that might convince you that it would be possible to teach a semester-long course in infinity category theory to undergraduates, assuming this homotopy type theory stuff was like down cold, you know, understood really well. Okay. So this is based on joint work with Mike Schulman. There's a paper that is included in the references at the end that I'll get to. And so we're using homotopy type theory as our background foundations, but the type theory that we're working in has a little bit of an extension of homotopy type theory. For those of you who are familiar with cubical type theory, this is a similar sort of extension to that, in that the contexts are going to be something a little bit more elaborate. For those of you who aren't familiar with cubical type theory, I should just say that type theorists are generally pretty flexible in what they mean by a type theory, and there's an idea that you should be able to sort of redesign your type theory to be particularly efficient for whatever setting you're working in, and that's the move that we're making here. So this is homotopy type theory like before, but my context, sort of the kind of background variables that I'm allowed to use are going to be a little bit more complicated in that I want to have these polytopes as part of the context. And you can say what a polytope means syntactically in a formal language. I'm not going to emphasize that so much. I'd rather you just sort of grant me that polytopes exist. But the way you do it is you can axiomatize a directed interval, which has two constants and this inequality relation. You should think of it as a directed interval in the direction from 0 to 1. And then you could imagine cutting out shapes inside that directed interval. So if I had, products of that directed interval with itself. So if I had a box, an n-dimensional box, inside that dimensional box, I could take the sort of the coordinates that satisfy this relation, and that'll give you an n simplex. So I've drawn the picture here of the 2 simplex, a triangle sat inside a 2-dimensional box. And I could impose additional conditions that say that your points here, S and T, aren't just in this 2 simplex, but are on the boundary of the 2 simplex, because one of these equations holds. Or I could say that maybe I'm along these 2 specified edges of the boundary of the simplex. So there are these geometric shapes that you can describe in a syntactic language that is built from this directed interval together with some sort of intuitionistic logic. But let's just pretend that these polytopes make sense, and I'll use only some very simple shapes below. And then I'm going to need one additional type forming operation. So this is another one of these like formation rules, and this is something called an extension type. And here's sort of how these extension types work. It says that if I were given 2 polytopes, psi and phi, and one of them should be a sub-polytope of the other. So you could think of like the boundary of the n simplex in the n simplex, or this horn thing, the boundary of the 2 simplex inside the 2 simplex, or maybe this horn thing inside the 2 simplex. So if I've given 2 of these polytopes and one of them's a sub-polytope of the other, and I had a term in a function type, so I had a function from the smaller polytope into some type A, then I'm allowed to form an extension type whose terms will then be functions from the larger polytope into A that restrict along the inclusion to the given term before. So this picture is meant to be kind of a cartoon of this extension type to help us remember what it is, because I realize this formulation is a little bit complicated. So the inputs to form the extension type are a specified function like this and a specified polytope inclusion. And then the terms of the extension type are functions here that restrict to the specified one. Okay, so here's why we need all of that. So I'm trying to develop the theory of infinity categories, and a highlight is I'm going to define an infinity category for you. So this is going to refer to, well, I guess the first definition we need is something that I'm given here. So using this extension type construction, I can define for 2 terms of type A, a type which I'm going to denote like this, hom A xy. And how it's given is as one of these extension types. So this is going to be the type of arrows. A term in this I'll think of as an arrow in A from x to y. And what is it? Well, so one of these polytopes is this shape delta 1, which ends up just being the same as this directed interval. A subpolytope is its boundary, which are 2 points. And so if I'm given a function from 2 points into A, that's just the data of 2 terms of type A. An extension of that to a directed interval, that's exactly kind of the geometric intuition for an arrow. So we're defining an arrow to be a map from a directed interval into A, whose source is X and whose target is Y. All right. So now that I have this type whose terms are arrows from X to Y and A, I can give a definition of what it means for a type to be an infinity groupoid that sort of connects back to this homotopy interpretation. And here's what it is. So a type is an infinity groupoid if a particular function that I'll tell you about momentarily from the identity type to the type of arrows is an equivalence. So what is this particular function? So I'm calling it path to error. It's some function that converts a proof that x equals y, or a path from x to y, into an arrow from x to y. And I can define a function like this by appealing to the path induction principle. So if I'm trying to define a term in this function type, by the introduction rule for function types, I can assume I have path P from X to Y, and then I need to define an arrow from X to Y. But by the path induction principle, to inhabit this type of arrows, it suffices to assume that Y is the same as X and P is reflexivity. So I really only need to define this mapping in that particular case. And there I can say that I want to define this function to be the function that sends the reflexivity term to the identity arrow, which I haven't defined for you yet, but it's coming, I promise. So there's a particular function, path to air, and if that function gives an equivalence between this type of paths and this type of arrows, that's what I'm going to say as an infinity groupoid. And that sort of makes sense. We had the sense already that any type can be thought of as an infinity groupoid, or its infinity groupoid structure comes from its identity types. So here in this sort of category world, if it's hom types, if its types of arrows are really just these identity types that we had before, then it does make sense to think of that type as being an infinity groupoid.
Sorry, so here it seems like you're defining infinity groupoids as a property of types, not structure. Is that correct?
Yes. Yeah, that's right.
Okay.
So, that's going to be true for infinity categories a bit as well. And that's a little weird. I should say, to justify all of this, we need, so this is kind of confidential to the graduate students or the experts. There's a model of everything that I'm going to say, which is familiar to people who work with infinity categories. This is the complete Siegel space model of infinity one categories. And complete Siegel spaces are certain types of Siegel spaces, which are certain types of redefibrant bisimplicial sets. And this is mirroring the observation that you just made. So the types will be the redefibrant bisimplicial sets in this particular model. A certain property of them will make them Siegel spaces, which I'll call pre-infinity categories in just a second. And then a certain further property will make them infinity categories. And it's a bit strange, but that's how the model works. So we want the theorems that we prove in this type theory to interpret in a place that mathematicians care about today, and that's kind of why we've set it up in this particular way.
And is it something we should expect, that it should be a structure, not a property, not a structure? Or is it?
No, you can think about that as a choice that Mike and I made, and you can imagine other people preferring to make a different choice.
Okay, thanks.
Okay, so the aim is to tell you about infinity categories. And what's kind of remarkable about this story is that I can define infinity categories at all. So there's a, last spring at the Mathematical Sciences Research Institute, there was this semester-long program on derived algebraic geometry. That's a community of researchers that might want to work with infinity categories, so they aren't experts in infinity categories. So there was an introductory lecture, a 3-hour lecture series, beautiful lecture series by Carlos Simpson, illustrating sort of what infinity categories are, why you would want to use them, where this higher dimensional structure comes from lower dimensional things. And it ended, the 3 hours ended with a definition of infinity categories. So that's kind of how hard it is to say what infinity categories are today. And here I can give a much shorter definition because these new foundations are really more amenable to saying what it is. But let me try to get there. So now I'm going to tell you, I mean, right, from some point of view, it's not impressive that I'm really excited that I can just define the thing that this talk is meant to be about. But from another experience, that is actually somewhat surprising. So,
I have a question. So you are saying here that, or you said before actually, that a type can be thought as of a space. Mm-hmm. But here you are singling out type of, or a type of types that are infinity groupoids. Mm-hmm. But the homotopy hypothesis tells us that spaces are infinity groupoids. And so should we think as a type as a simplicial set, so that not all are infinity groupoids, or?
Right. So, I mean, what's a little subtle here is there's lots of different possible interpretations so there are lots of different models of homotopy type theory. There are lots of different interpretations. And it's hard to answer your question without getting a little too deeply into the semantics. So what this I guess this notion of infinity groupoid, we'll see later, is that this coincides with the infinity categories in which all arrows are invertible. So it's a little bit, right, it's a little bit more structured than the background infinity groupoid. This is kind of a subtle question, so maybe I won't sort of say anything more about that. But,
okay, thank you anyway.
Sure. But no, I mean, in the models, the types are really more like complexes rather than arbitrary simplicial sets. Okay, so let's try and say what a pre-infinity category is. So there's, this is going to be most of the way to a definition of an infinity category. There'll be one additional piece that comes along. For those of you who are familiar with semantics, these are the Siegel spaces, but not yet the complete Siegel spaces, and that's what this pre is referring to. So we're going to say that a type is a pre-infinity category if every composable pair of arrows has a unique composite. And the key point here, and this is why we're really starting to make use of these new foundations. Uniqueness is now in the sense that we discussed above. Uniqueness means some type is contractible. So the definition, a type is a pre-infinity category if every composable pair of arrows has a unique composite. What this means is if the type that says, the type that says, here's the data of a composite of a composable pair of arrows is contractible. So an elaboration of this says that if F and G are arrows, F from X to Y, G from Y to Z, the fact that this Y is that Y is what composable means, then I'm entitled to form this extension type. Here's a cartoon for you. So this is one of these polytopes. This is the polytope that corresponds to a particular directed boundary of the two simplex. That's a subpolytope of the two simplex. And what I'm saying is the type of two simplices that extend this horn, that extend this composable pair is a contractible type. That's the technical meaning of this informal sentence. Every composable pair of arrows has a unique composite. So the type of two simplices in A that extend the data of this given composable pair is contractible. Okay, so what are we going to do with that? So firstly, if a type is contractible, what we know is that it's inhabited. So I definitely have a term of this type. So under the hypothesis that A is a pre-infinity category, if I have a pair of arrows F and G, I get a term of this type. And I'm introducing some notation here for the term of this type. So really a term of this type is a function from this two simplex into A. So it's like this entire triangle here, where part of the boundary is given by F and part of the boundary is given by G. I didn't tell you what the elimination rules are for these extension types, but had I done, you would see that I could extract out from this function a thing like this, and I can restrict to just this edge. So from a term of this function type, I get an arrow from X to Z. So this would be a term in hom A X Z, and that's this, what I'm denoting by G circ F. So from the hypothesis that I have a unique composite, in other words, a contractible type here, I get various terms. One of the terms is this two simplex, which I've drawn here. And another term is a particular arrow from X to Z that I've called G composed F. Now, this data is not unique, again, in the sense of classical mathematics. So it's not the case that in an infinity category, as if I were trying to describe what an infinity category were to you using classical foundations, it's not at all the case that any composable pair of arrows has a unique composite. That's not true. But what is true is that any composable pair of arrows, there's a contractible space of choices of data of a composite. And that's exactly what I get, what uniqueness means in this homotopy type theory context. So this type may well have other terms. In fact, it quite likely does have other terms. But what contractibility means is that if I were given some other term of this type, then I could prove that that term was equal to the one that I've specified previously. And in type theory, you're allowed to sort of substitute along equal things. This is kind of related to this path induction principle. So I can pretend I guess the upshot, the informal upshot is I can pretend that I just have one term of this type. I can pretend that I have a well-defined composition operation that goes from my F and my G to my composite arrow G composed F, even though that's not true in the sense that we ordinarily understand it. It is really true in these new foundations, and this is part of why these new foundations are sort of so powerful from this perspective. Okay, so let's try and get used to this idea by proving some lemmas. So I've given a definition of a pre-infinity category that's really pretty sparse. It says that every composable pair of arrows has a unique composite. So for any F and any G, I have some contractible type, which gives me these terms. I haven't referred to identity arrows, though I guess implicitly it's there, and I haven't referred to associativity of composition. And what's nice is those things are actually going to follow formally. So what I'm going to prove for you now is that every term in type A has an identity arrow that then acts as an identity for composition. So the first thing I'm going to do is I'm going to construct this identity arrow, and then I'll prove that for any arrow from X to Y, or you could imagine an arrow from W to X, that F composed with the identity, where composition is defined up here by this pre-infinity category axiom, I'm going to construct or prove that F composed identity of X is equal to F. So this is proving the identity axiom in a pre-infinity category. Okay, so the first task, again, is firstly just define this identity arrow at all. I'm going to use the introduction rule for these extension types that I didn't tell you about, but it's similar to the introduction rule for the function type. So to produce, so an identity arrow, again, should be a term in this hom type, which was defined as one of these extension types. So in other words, I need to define a function from my polytope, my directed arrow polytope into A. And that function needs to start at X and end at X. There's a particularly simple function that starts at X and ends at X. It's just this constant function. So in the Lambda abstraction, it would look like this, but you can, the constant function does satisfy the rule of being a term in this extension type, and that's how I define the identity arrow. So geometrically, I'm thinking of the identity arrow as just the constant function at X. Okay, so that gives me the identity arrow and makes rigorous this definition of infinity groupoid that I had above. Now, I need to prove further this composition relation. So I'm going to assume that I have a arrow F from X to Y. What I want to prove now is that F composed identity at X is equal to F. So the way I'm going to do that, so firstly, this is the extension type that governs the composition relation F composed identity. And I'm going to construct a particular, well, and by the sort of contractibility assumption that any composable pair of arrows has a unique composite, there is a unique term in this extension type, and it's the one that defines the arrow F composed identity at X. But I can construct another term of this type, again, using the introduction rule for extension types. So I'm going to define for you another map from the polytope that's this 2 simplex into A. And I'm going to define it again by this lambda abstraction. So remember, this is sort of a subshape of the sort of directed square 2 times 2. So I have coordinates for that S and T. And I'm going to project onto just one of the coordinates and apply the function F. So this is some formula that refers to the syntax that governs these shapes. And it's, you can check that it does in fact define a term of this extension type that sort of looks like this. It'll have the identity arrow along one boundary, the arrow F along the other boundary, and crucially, it has the arrow F along this boundary here. So what I have now is I have 2 different terms of a contractible type. I have the one that I hypothesized to exist by saying that I had a pre-infinity category, and that defined what I meant by this notation F composed identity X. But I have another term that I've just constructed, which is given here, and the boundary arrow in this case is this F. But because this type is contractible, these terms must be equal. I must have a proof of equality that says that F composed identity of X is equal to F. And that's the end of the story. So here I've constructed a witness that F could well be regarded as the composite of the identity with F, and that means that F is the composite because by uniqueness there is only one composite. Okay, so again, this all takes a little bit of getting used to, but once you do, it's kind of cool. And then there's a proof of associativity along the same lines. So I didn't need to ask that composition is associative because you can actually prove it. So what the statement says is if I have 3 composable arrows now, I could use this sort of unique composition thing to define what I mean by G composed F and then H composed G composed F. Or I could first compose H and G and then compose with F. And these will be 2 different arrows from X to W in A. And I can prove that those 2 arrows are equal. So the proof of this is a little bit geometrically more sophisticated, and it relies on a lemma that you'd also have to prove that says that if A is a pre-infinity category, then, so A is a type that's a pre-infinity category, then so is the type of functions from the arrow into A. And so what's cool about that is now that I know that this is a pre-infinity category, I can say that any composable pair of arrows in here has a unique composite. And what this picture is illustrating is a composable pair of arrows in here. So these would be arrows in the pre-infinity category of arrows in A. So an arrow of arrows is really a commutative square. So that's what's drawn here. Here I'm taking F and G and their composites, G and F, and this is a commutative square of arrows of arrows. And then I have another commutative square involving G and H, which is using the composite H composed G. And when I compose them, I'm now going to get a 2 simplex of arrows, or in other words, this sort of prism-y shape. And if I look at this 3 simplex that sits inside this 2 simplex, and I look at the faces of these 3 simplexes, what you'll see along the back is there's a 2 simplex face that has F as one of its boundary edges, H composed G as its other boundary edge, and that means that the diagonal is necessarily H composed G composed F. But then that diagonal edge was the same as the diagonal edge for another 2 simplex face, which is G composed F and H. So that 2 simplex witnesses that this boundary edge can be regarded as the composite H composed G composed F, while simultaneously it can be regarded as the composite H composed G composed F. And that's the sense, or that's the sort of strategy for proving that these 2 composites are equal. Okay. Let me end with a definition and a statement of a theorem, and then I'll take further questions. So I haven't yet defined infinity category for you, but we're really very close. So there's one additional axiom in an infinity category, and what it refers to is a notion of isomorphism in a pre-infinity category. And the definition of an isomorphism is very similar to the definition of an equivalence that we stated previously. So an arrow from X to Y is an isomorphism if it has left and right composition inverses. So in other words, the type of isomorphisms from X to A is defined to be the type whose terms are firstly an arrow from X to A together with 2 arrows from Y back to X, so that the composite each way around is equal to the identity. And as before, if you had a term of this type, you could then prove that G and H are equal. But the reason for preferring to define the type of isomorphisms this way is because this part of the type is now one of these mere propositions. So if F is an isomorphism, it's an isomorphism in a unique way when given this particular data. Okay, so we're going to say that a type A is an infinity category if, firstly, every composable pair of arrows has a unique composite. So this was the pre-infinity category axiom that we had previously. And then secondly, there's something that goes by the name completeness condition, which says that isomorphisms are equivalent to identities. And so what that meant is this is very similar to this infinity groupoid axiom. For all x, y, and a, we have this function path to iso, kind of like we had this function path to air, which by the path induction principle is defined by just saying that I'm going to send reflexivity to the identity. So you need to prove that the identity arrow is an example of an isomorphism, but that's not so hard to show. And to say that something is an infinity category, I say that isomorphisms are equivalent to identities in the sense that this arrow is an equivalence. And I'll end by just displaying the statement of this theorem that relates the notion of infinity groupoid that we had previously. it turns out that a type is an infinity groupoid, sort of if and only if a type is an infinity category in the sense of the definition given here, and all of its arrows are isomorphisms. And maybe I'll let you read the proof on your own. Thanks very much. That's a good place to stop, and I'll invite further questions. So I guess maybe I'll take questions first that people don't mind having recorded. But I will turn off the recording at some point and we'll have questions else. I forgot to say the slides have been available this whole time. So if you want to have a look, they're on the web. Maybe I'll display the references page as well.
I have another question that's related to the fact that being an infinity groupoid is a property, not a structure.
Sure.
It seems like there are two simplicial directions, like homotopical directions,
right.
And that by this fact you're actually merging them in a way. Is that something like that you can comment on, or?
Yes, that's right. So there's an intended model for the type theory that I just discussed, which is this complete Siegel space model as bisimplicial sets. And in that particular model, everything that you said is exactly true. So bisimplicial set means there's two different simplicial directions. One you think of as the categorical direction, and the other one you think of as sort of the space direction. What this completeness axiom is, so the second axiom that says that isomorphisms are equivalent to paths, it says that the sort of paths in the spatial direction coincide with the isomorphisms in the categorical direction. So that's sort of what's tying together those two different dimensions. And then the groupoid condition is saying that in addition, all of the arrows in the categorical direction are in fact visible in the spatial direction as paths.
Okay, thanks.
Sure.
Can I ask you a question about the definition of directed cubes?
Sure.
You say that they are a product of the directed interval 2.
Mm-hmm.
And all we know about this interval is that it has elements 0 and 1 and an order relation.
That's correct, yeah.
What are the rules for this interval in type theory? Because it's not just the Booleans.
Right, that's right. So
assuming that there are other elements between 0 and 1.
Right. So yeah. So I mean, really, the thing I should say is you should look at the paper where we sort of spell this out in full. But right, all that's so the interval is axiomatized sort of in exactly that way. So we have this. I guess it's sort of the directed interval axiom. So we have axioms that says that for all terms in the directed interval, whatever they are, 0 is less than or equal to the term, and the term is less than or equal to 1, things like that. I guess I don't know quite what to say. So these polytopes sort of, I mean, they're a little bit weird in the theory. In the model, they do end up being types, but we shouldn't really think of them as being types in the type theory. So these are sort of defining shapes that it's kind of valid to map out of. And that's, yeah, it's a little bit confusing. So, yeah.
Would this approach? Oh, sorry.
No, it's not really about the presentation, but it's more about the introduction. You say that in the future, we will learn to undergraduate students infinity category. And why do you think that? Yes. So what are our arguments for you that infinity category could be teach to students, to undergraduate students. So sorry
Right.
for my bad English.
Sure, it's okay. So it's the question, why would anybody care about infinity categories? Why should we teach infinity categories?
No. Why could we teach it? Because it seems very an abstract theory,
Right.
instead of abstract algebra, which is more
Sure.
simpler, I think.
Right. Fair. Yeah. Okay. Sure. Fair enough. So I should say this talk was really meant to be very speculative in a number of different ways. So absolutely, it's certainly possible that in 100 years we won't be teaching infinity category theory to undergraduates. I mean, a counter argument for any of this would be the fact that we don't teach category theory to undergraduates today, typically, even though, I mean, obviously my point of view is biased, but I would argue that category theory is, kind of an increasingly important part of mathematics, and yet we don't teach it to undergraduates. So similarly, it's certainly plausible that we won't be teaching this material to undergraduates ever. But I thought it would be fun to imagine if we were to teach infinity category theory to undergraduates, how might that come to pass? And that's sort of what this is about.
Okay, thanks.
Is it reasonable to expect that such a way to define infinity categories could be used for infinity categories which aren't infinity one categories, or is it unreasonable to expect something of the sort?
Right. I think that would be awesome, because there's even less. So I should say the thing that isn't speculative about this is, there is this paper, which is what the second part of the talk was based on, it sort of explains in more detail the type theory with these polytopes and these directed cubes, which I didn't present very well, partially because I'm not a type theorist, and also how to interpret this in a model of infinity categories, or in sort of a setting for developing infinity category theory that people work with today. So this does give a way to prove theorems about infinity one categories. It would be really wonderful if we had a type theory that allowed us to prove theorems about infinity two or infinity n categories, because that theory is much less developed. My instinct is you would have to start with a different kind of modification of the homotopy type theory. So like here we introduced these simplicial shapes and these directed polytopes. Maybe you'd have to introduce something like the theta n, which is this category that indexes the compositions in a higher category, like delta indexes the compositions in a one category. But nobody's done that yet, so that's an open problem. And if you'd like to think about it, I'd really encourage that.
Okay, thank you.
I also have a question about this speculation aspect. Basically, I feel that maybe one of the most complicated things to approach this area is what you mentioned about there being many models and interpretations of everything. So do you think in this speculation where undergraduates are taught infinity categories, would it be that in this world, people have actually converged to one particular model that is like always used, at least in introductory situations, or like in a standard way, so that it's easier for people to approach it? Or would it be that everyone gets used to thinking about various models all the time, and like that's included in the like basic intuition for mathematics?
Great. I'm really glad you asked that question. I should have said something about this in the talk. So the way that, let me explain sort of how infinity categories are worked with today. I mean, I can tell that you know already, but just for everyone else. It is.
I don't really.
Well, so it's really hard to say what an infinity category is in set theory. And sort of the moral reason for that is there's just not a lot of sets involved in infinity categories. So so firstly, even an ordinary category doesn't really have a well-defined set of objects, because sort of morally you should only ever work with categories up to equivalence, in which case you don't have a well-defined set of objects. So there's that issue, and then there's a compounding one. In an infinity category, between any two objects you should have a space of arrows, but that space is really only well-defined up as to a homotopy type or as an infinity groupoid up to equivalence. So it's kind of hard to say what that is. And then composition isn't a function with a unique value. It's sort of a function that's valued in some contractible space of choices. And there's just kind of not a lot of sets or sort of functions or Bourbaki style mathematics involved in infinity categories. So what these models of infinity categories refer to is their ways to make precise in sort of classical set theory what it means to say that you have some objects and some arrows and some higher arrows and some higher arrows, and you have composition that's sort of weakly well-defined up to some higher arrows those compose in a sense that's weakly well-defined up to higher arrows, and you have some weak invertibility. And so these models are sort of ways to make all of those ideas precise. The experts or sort of researchers in this area have always had a sense that the models are really beside the point. So people have always wanted to work with infinity categories model independently, but it's until recently it has been unclear how you could do that rigorously in a set-based system. So I think, so you're correct in intuiting that my vision for teaching infinity category theory, or whether or not we're teaching this to undergraduates, my vision for infinity category theory 100 years in the future is that models will be completely beside the point, that we'll have perhaps because we have some sort of improved foundations, we'll have we'll be able to think about infinity categories sort of as they really are without spending so much time worrying about the different sort of presentations of an infinity category in a particular model. And people would be glad of that development, I think,
Yeah, that sounds like it would be great.
Yeah.
Yeah, thank you.
I should, maybe one other thing I should mention, there's another kind of synthetic approach to infinity category theory that sort of is a mature technology today, and that's described in another joint project of mine with Dominic Verity. We're writing a book about this. So this is the audience for this are really, sort of graduate students and researchers who want to work with infinity categories now and have a very solid one category theory background. But this does give a way to work model independently with infinity categories, sort of using classical foundations. So set theory is the ambient meta theory in this case.
Awesome, thank you.
I have what I think is my last question.
Great.
So you mentioned a couple of times the intended model were Siegel spaces or complete Siegel spaces. I wonder how far you've gotten in actually relating notions in your synthetic approach to the actual, like the models. So for instance, if you want the notion of limits in complete Siegel spaces, is it the same as the notion of limit you could define with your synthetic approach?
Great.
Like,
yeah, so thanks for the question. So what we've done, so we've developed sort of basic theory kind of along the lines I've discussed here. We have a reasonably comprehensive theory of adjunctions, where the data of what witnesses the fact that a functor is a left adjoint is presented in a number of different ways, some logically equivalent ways, and then some genuinely equivalent ways. We have a theory of what infinity category theorists would call left fibrations, but we call sort of covariantly functorial type families. This has to do with the Yaneda lemma. There's a little tiny bit of that here. There is a proof of the Yaneda lemma, and in fact, a proof of something called the dependent Yaneda lemma, which is a better Yaneda lemma than I was aware of being true, which here I've described as a principle of arrow induction. We do not have anything about Cartesian fibrations, though that has sort of more recently been developed by Ulrich Buchholz and Jonathan Weinberger. We do not yet have any theory of limits and colimits, though somebody's mentioned to me that they might give that problem to a student for their PhD thesis, so that might be coming soon. And in general, I'd say there's relatively little sort of sophisticated category theory in this setting. There's one big technical open question which has to do with the issue of universes that are appropriate for classifying these different sort of fibration notions, and that's also, there's work in progress, though not by us.
Okay, so in the coming years, we might get to see like a theory of limits and co-limits in this setting.
Yeah, I think that would be really wonderful. We won't be the ones to do it though, so somebody should take that.
Okay.
So,
okay, thanks. Thank you very much. It was a great talk.
So there was something that confused me. So you said that you work in an extension where types are allowed to depend on polytopes.
Yeah.
And in what follows is, when you say type, does that mean that type implicitly means something that depends on a polytope, or so my interpretation is that from this point on, type means really a pre-sheaf of types on a category of polytopes. Is that correct?
Right, that's a good way to think about it. So in the so yes, this, and what I'll say is a little bit different, but is consistent with your intuition. So the usual, so this is relating again to like the categorical semantics of the type theory. The usual way, so if your context was empty, so if there's sort of no variables or types in the context, then when you interpret a type, you interpret it as an object in a category, or if you have this homotopical interpretation, it's a fibrant object, whatever that means. And then if you have a dependent type, so if you have a type family B that's dependent on a type A, or so the context has this type A, then you interpret that as a fibration or a map over A. So you're working in some slice category. So here, these polytopes appear like in the base, and the type that's dependent on the polytope is a type over, or is a thing over that base. So the reason this was consistent with the pre-sheaf interpretation is really the category we're interpreting in is this category of pre-sheafs. These are these bisimplicial sets. And when you slice a pre-sheaf category over a fixed object, that's equivalent to another pre-sheaf category where you sort of add into the pre-sheaf the category of elements for the fixed object that you sliced over. And in fact, it's better to think about pre-sheafs than these slice categories, because the substitution operations are stricter there. So from the point of view of the model, that's actually the best intuition to have. So the TLDR was, you were right. Yes, that's correct. No.
Thank you. That makes sense.
Sure. And I should say, I didn't describe this type theory very clearly. I mean, partially because I'm not a type theorist and I'm not so fluent in the language, but I should say we want to keep these shapes sort of apart from the types, because this has to do with the computational aspects, which I haven't really emphasized all along. We want the data of a term in here to be something whose restriction to the boundary or restriction to the subshape is really sort of computationally equal, very strictly equal to the given function, just because otherwise the data involved in the types proliferates kind of uncontrollably. So this now has to do with sort of technical aspects of certain things being cofibrant and certain things being fibrant. It turns out these shapes end up being both sort of fibrant and cofibrant, so we can think about gluing them together strictly, but we could also in fact map into them if we really wanted to. But yeah, there are some technical things to be aware of in setting this all up correctly.
A question from the bottom of the class here. If you go back to the homotopical interpretation, when you were saying that x equal y, and if I were to think about visualizing that, I would have expected x and y to be overlapping each other in kind of a visual in the space, but they're stretched apart here. And I'm curious as to what that gives us. And it seems like it's playing with the notion of what it means for things to be equal to each other, and allows for different variants of that. Is that? Fair.
Yeah, that's great. So your intuition is the intuition that people had for a very long time, that if you have a term in an identity type, then what does that mean? That means X and Y are really equal. They're the same. In the picture, they should be the same point. So that was definitely the intuition that people had for a very long time. What this homotopical interpretation refers to as a new intuition. Let's sort of imagine, instead of equal meaning the 2 points were the same, meaning there's sort of a continuous way to move from one point to another. It's sort of a new imagination. And it turns out that this new intuition, in a sense, sort of better reflected what was going on in the rules of the type theory already. But it's definitely a new way of thinking about equality. And, there's a lot of interesting kind of philosophical considerations with that. So one of the references I've mentioned here, this is this essay of Mike's, Homotopy Type Theory, a Synthetic Approach to Higher Equalities. It's in a book of Elaine Landry, Categories for the Working Philosopher. And a number of the essays in that book concern aspects of homotopy type theory and really discuss in some detail sort of what these sort of new intuitions are. So it sounds like this might be an essay that's nice to read.
Thank you.
A quick question real quick. You mentioned for the working philosopher. What were you referring to?
So this is a book of essays edited by Elaine Landry. It's called Categories for the Working Philosopher. And I particularly recommend this one, but there are actually a number of essays in there are very nice.
Got you. Thanks.
If I may, here we wrote in homotopy time theory, and I was wondering, I know there are different kinds of foundations based on dependent types theories that are more or less equivalent to homotopy time theory, and I'm particularly thinking about cubical type theory, which takes as an axiomatic definition the existence of an interval type, which is more of a pre-type, and then goes on as defining a path as a function from the interval type into any other type, and then defines concatenation and other general principles using horn fillers. Couldn't all that, I thought about that when you talked about these ideas of polytopes. Wouldn't it be more natural to see this definition of infinity categories in a setting such as cubical theory?
Great. So yeah, so absolutely there's a lot of similarity between this sort of simplicial type theory that we're using for infinity categories here in cubical type theory. And whether there's a way to develop infinity category theory in something like one of these cubical type theories is an active research area. One of the things that is kind of an open question is whether there's sort of a good model of infinity one categories, sort of in the sense of classical mathematics, that's based on one of these cube categories. I mean, there are ways to transfer the model structures for quasi-categories or for complete Siegel spaces to cubical presheaves instead. There's sort of formal ways to transfer these model structures, but those formal ways don't necessarily give you a nice characterization of the fibrant objects, so you don't necessarily know exactly how to think about infinity categories as cubical sets. So that's one of the sort of open research areas. So I think the reason that I'd say it's not more natural from this point of view is that on the categorical semantics side, it's not really well understood how to think about infinity one categories as something that are governed by cubical shapes rather than simplicial ones. But you're not the only one who has this idea, and people are working on it.
Okay, thank you very much.
Sure. All right, I might turn off the recording if I can figure out how to do that.